All right. So let's get started. We got it's 4:05. This is COMP2804, Discrete Structures 2, and I'm the instructor, Daryl Hill. All right, so I guess update on the test. They're all sorted. You can come by. I prefer if you come by during office hours on Thursday. But if you can't make it, then just email me and we can arrange a time for you to come see your test one. Other than that, we're here. Oh, happy Valentine's Day, I suppose. Yeah. So I didn't get you anything, I'm sorry, but there is a holiday coming up. So this is the last week. Your assignment 2 is due after the break. Again, it should be here. So it is due the Monday night. I'm not sure if the date on the assignment reflects that. I'll have to double check, and I keep forgetting. But so yeah, not much going on other than we're starting probability today. But any questions? Yeah.
This assignment 2 be doing the same as assignment 1, like the day after 8 a.m.
Yeah. So yeah, you can try and get it in under the wire, but please upload something like well before the deadline, so you don't get stuck. Because yeah, if it's after 8, if it's 8:01, it's 0. So get something in before then. Other questions? Okay. All right. So today we're going to start talking about probability. Oh, that's okay. All right, so we're going to start talking about probability. And when I'm our office hours, my office hours are Thursday at 10 a.m. Generally, I keep the door open for an hour, but I'm flexible if people drop in after that. So on busy weeks, I don't mind spending more time. That's just sort of 1 hour is the suggested time. Yeah, so on Thursday. Okay, so we're going to talk about probability, or start talking about probability. It's going to have a lot of counting in it. But before we get started, we're going to look at a neat little problem in probability. So yeah, this chapter is where it's there's some fun problems we can solve here, and there's some unexpected things. It's basically the chapter where we learn how to gamble, and then next chapter we learn that you should not gamble because the house always wins. But yeah, so, oh yeah, here's the other thing I was supposed to let you guys know. There's going to be a blood drive. Well, it's on the slides. You can look it up. So it's on Wednesday, March 1st. And I guess you have to make an appointment. I will probably see if I can do that. But yeah. So before we get started with probability, we're going to look at randomness and some of the sort of interesting things you can do with it. And then later on, actually, we also prove a lot of other interesting results that have nothing to do with probability. But for this problem, we're going to talk about anonymous broadcasting. So I'll explain the problem in a moment. But right now, you probably have seen some probability. You took it in high school or whatever, and you have some intuitions about how to apply it. Right, so if you flip a coin, it's about 50-50, and what 50-50 means is that basically if I flip it 1,000,000 times, then it's going to be pretty close to half the time it's going to come up heads. So yeah. And if I flip a coin and I don't show you the coin, that means you won't be able to guess it very well, right? So you might get it 1 out of every 2 times, you might guess right, purely up to chance. You might also realize that you're not likely to win the lottery. We'll talk about just how unlikely that is. And when the weatherman is calling for an 80% chance of rain, you're probably going to see some rain, although you never know with the weatherman. So yeah, so we're going to take all of those intuitions, but we're going to basically start from scratch, redefine probability from first principles, which is basically using counting, right? So all the things we've been taking up until now, we've been sort of learning the foundations for probability. So there's going to be a lot of sets and stuff, but we're going to start with an example. This is just it's an exercise to get us into the right mindset. You're not going to be tested on it directly, so just try to understand it. Some of it gets a little heavy, of course, as always, but all right. So anonymous broadcasting. So let's say there's a problem. The group of 3 cryptographers are dining at a restaurant, and they're very suspicious of the NSA. So the waiter comes along and informs them that somebody has paid for their meal, which they're fine with as long as it's one of them. But it's also possible that the NSA paid for their meal and because they were listening in or whatever. So they want to figure out, without violating anyone's privacy, they want to figure out who paid for the meal, if anyone. So that's the essential problem here. So they're going to devise a system to announce, so somebody can announce anonymously that they've paid if they did indeed pay. And only one person would have paid, so only one person would be sending a message at any given time. So we're going to solve a similar problem that we could use to solve this problem. So our problem is, if we have a group of people on a network, we want anyone to be able to broadcast, right? So broadcast messages, send bits basically over the network. So one person broadcasts, and then everyone receives the message, and no one knows who sent it, right? So we're going to devise an algorithm that sort of hides who's sending these messages. So, and on our network, we're talking in binary, of course, it's a computer network. So we're going to transmit either a 0 or a 1. So, and 1 bit at a time, right? So this is sort of a protocol that could be used to, we could transmit more bits over a longer period of time, but 1 bit at a time. Okay, so, and we're going to explain it for 3 people because that's the simplest. Of course, you could generalize this for larger groups of people. Okay, so we have 3 people, P1, P2, P3. One of them broadcasts a bit B. To start with, we're going to assume that B is equal to 1, and then we'll talk about what happens if B is equal to 0. So yeah. So here's the problem. We have 3 people, P1, P2, P3, on a network. One person broadcasts a message. Everyone receives it, but nobody can figure out who sent it. Yeah, so that's our essential problem. And yeah, so in our example here, P1 wants to send this bit B. He wants P3 and P2 to receive this bit and not know that it was from P1. Okay, so in our problem, if someone paid for the meal, if we're back to the dining cryptographers, if someone paid for the meal, they're going to transmit a 1, and everyone else will transmit a 0. So if 1 is communicated, that means that somebody at the table has paid. If they receive a 0, if nobody transmits a 1, then the NSA has paid, right? So that's the problem. Everybody understand the problem? Okay. Okay, so to start with, we're going to look at every consecutive pair of people, and by pair, I mean sort of, if you imagine them sitting around a table, then they're all beside each other, right? So P1 and P3 are beside each other, P1 and P2 are beside each other. Of course, it's only 3 people, so everyone's beside everyone, but if we had more people, then those connections would not be quite, it would not quite be the complete graph. So every pair of people is going to generate a random bit and share it, right? So P1 and P2 will share the bit B1. Now, when I say bit, of course, I'm talking about 0 and 1. So it's simply a random bit with probability 0.5, it's a 0, probability 0.5, it's a 1. P3 and P2 share the bit B2, and P1 and P3 share the bit B3. Okay. So now everybody knows 2 bits, right? So P1 knows what the value of bit 3 is and the value of bit 2, but they do not know the value, or sorry, the value of bit 1, the value of bit 3, but they do not know the value of bit 2, right? And likewise, the same for everyone else. P2 knows B2 and B1, but not B3. So there's some information that's hidden from everyone, and that's going to be crucial in being able to communicate anonymously. Okay, so the algorithm then is everyone is going to take the 2 bits that they know, and they're going to add them together mod 2. So let's talk about mod 2 for a second, what that means when we're adding bits together. Basically, if I add 0 plus 1 mod 2, well, that's basically if I divide that by 2 and I take the remainder. So 0 plus 1 mod 2 would be 1. 1 plus 1 mod 2 would be 0. So sort of one way to think of it would be if I take a 0 or a 1 and I mod it with 1, it's going to flip that bit, right? So I start with 0 here. I add 1 mod 2, it flips that 0 to a 1. If I start with 1 here and I add 1 mod 2, it's going to flip that bit to a 0. So it's one way to think of it. Or if I add 0, of course, that's like the identity. I just get back whatever bit I had initially. Okay, so we're going to be doing a lot of this sort of math, the mod 2. And if I take 0, add 1, well, I flip it to a 1. If I add another 1, I flip it back to 0, right? So 0 plus 1 mod 2 is equal to 0. Or for instance, I can add another 1 and flip it again. So that's equal to 1. So we're going to do a lot of math that looks like this. It's sort of simple once you get the hang of it, but any questions? Yeah. What's that? Sorry? 3. Right. If I just, well, I mean, I was talking about flipping bits, but I guess we could just talk about mods more generally. If I add all these together, I get 3, and then I take mod 2. Well, then I divide 3 by 2, I get 1 remainder, right? So this is equal to 1. So you can, I mean, I can add arbitrarily long strings, but I only ever get a 0 or a 1 in return. And it basically, if I have an odd number of 1s, I get a 1. If I had an even number of 1s, I get a 0. Yeah. So that's, yeah. Oh, I think I changed these numbers, but I didn't change my answer. Yeah, so that's what it should be. Yeah, sorry. Other questions? Okay, so we're going to do a bunch of stuff like that, just so you're aware. So everyone adds their bits together mod 2, and whoever's transmitting, and we're assuming that there's transmitting a 1, adds their 1 to their bit, right? So if person 1 is transmitting, they're going to take their 2 known bits, B1 and B3, add them together, and plus B, and take the answer mod 2. That's going to give them a 0 or a 1, and that's going to be what they transmit. So this will be what person 1 transmits if they're transmitting the bit. Everybody who's not transmitting the bit will simply add up the 2 bits that they know, these 2 random bits, mod 2. Okay, so P3, P2. We'll go over an example with actual numbers in a second, but just to explain the algorithm, we'll stick with variables. So yeah, everybody computes the bits that they know. The person transmitting adds 1 to that. Everybody computes mod 2, and then everybody transmits to everyone. At this point, everybody can see. So as P1, I can see P3's number and P2's number. P3 can see P1 and P2, etc. So everybody can see what everybody's transmitting at this point. All right, so then I take, well, P1 plus P2 plus P3, well, that is, if I look at all the components, right? So P1 is B1 plus B3, P3 is B2 plus B3, P2 is B1 plus B2. And if I expand all of those out, right, because I'm summing all of the transmitted bits, if I expand them out, I get this plus the transmitted bit mod 2. Okay, so here's where sort of our little magic comes in. Our claim is that this is equal to B mod 2, which is just B. Okay, so if we add all of these together, mod 2, along with our transmitted bit, we're going to get back just the transmitted bit. And nobody knows who sent it, but we'll talk about all of that. So why does this work? So this is my claim. I haven't proven it yet, but let's talk about why that should work. Yeah, A is the transmitted bit B. So if I look at what I've computed, P1 plus P2 plus P3 mod 2. Yeah. So what I've added together is, if I expand out P1 and P2 and P3 and then gather my like terms, well, I have B1 plus B1 here. I have B2 plus B2, B3 plus B3, and then the transmitted bit, all mod 2. So if we look at what happens when I add a bit to itself, mod 2, well, what happens is that any bit added to itself, mod 2, gives me 0. In some sense, I'm multiplying by 2. If you're more comfortable with bit operations, basically that's a, what is that? It's a left shift, right? So then I end up with a 0 in my ones. So for instance, if BI is equal to 0, then BI plus BI mod 2 is 0 plus 0 mod 2, which is 0. Yeah, 0 mod 2, which is 0. If BI is equal to 1, then 1 plus 1 equals 2. Mod 2 is also equal to 0. So the fact that all of these randomly generated bits appear twice here means that they all cancel themselves out, and I'm simply left with plus B. All of this mod 2, of course. Right? So these all add up to 0 mod 2, and I'm simply left with whatever I transmitted. All right, questions? Again, we're just warming up to some probability here, but okay. So let's look at an example, just so we get a better sense, and then we will sort of walk through. We'll hand wave a proof because it's a little long, but every pair of people flips a coin. So let's say that B1 is equal to 1, B3 is equal to 1, B2 is equal to 0. And then we will look at an example where P2 is the broadcaster and P2 wants to transmit a bit 1. Okay, so P1 computes the 2 bits that P1 knows, B1 and B3, mod 2, right? P1's not transmitting, so we don't worry about B. P2 computes the 2 bits that P2 knows, so P2 is here, B1 plus B2 plus B mod 2, and P3 computes the 2 bits that P3 knows, B2, B3, mod 2. So if I look at all of those, P1, B1 plus B3, well, that's 1 plus 1 mod 2, that's equal to 0. P2, I have B1 is 1, B2 is 0, plus B is 1, right? So that's 2 mod 2, which gives me back 0. And P3, I have B2 is 0 and B3 is 1, mod 2, that gives me 1. So I've computed P1 is 0, P2 is 0, P3 is 1. Now everybody transmits those computed bits. All right. So I sum all of these together. So that is 0 plus 1, or sorry, 0 plus 0 plus 1, or whatever order you want to do it in, it doesn't matter. I take that mod 2 and I get 1, which is equal to B, the transmitted bit. Right. Okay, so that's our example. We will look at if B was a 0 in a second. But yeah, somebody's got a question. Yeah, so P2 wants to secretly transmit a bit B. In this case, we're assuming B is 1. It could be that B is 0, but we know that every round, only one person is transmitting, and they could transmit a 1 or a 0. So when we add up P1 plus P2 plus P3, everybody gets the next bit in the message. Right, so that's why P2 adds in B along with theirs, because then when we add up P1 and P2 and P3, we end up with B as the answer. I don't know, does that answer your question? All right, yeah, hopefully. If not, again, we're trying to warm up here. This is not really testable material, but it's a good introduction. Okay, so we can broadcast in this way, and each person can extract the bit B, right? It's always going to be a 1 if we transmit a 1. But the idea is that we want to broadcast anonymously, so let's convince ourselves that this P2 has broadcast, and let's say that P1 has no idea if it was P2 or P3. P1 knows it wasn't themselves, so they know it must be either one of these two guys. So the proof is actually brute force. I'm not going to, we'll just talk about it at a high level. I'm not going to go through all the steps, but we will look at this particular example and show what happens. Why P1 can't figure out if it's person 2 or person 3. So P1 saw that P2 transmitted this bit, P2, right? So it's 0. And they also saw what P3 has transmitted, and P1 also knows what they transmitted. P1 also knows these 2 bits, but P1 does not know B2. Okay, so when P1 does its calculations, it looks at how P2 might have been calculated by person 2, and they know, well, it's B1 plus B2. If they transmitted, then they added in B, and then mod 2, and then that gave them an answer of 0. Likewise, person 3, I take bit 3 plus bit 2 plus maybe B mod 2, and that gives me an answer of 1. So they know that what the result is, and they know some of the information. If they try and figure out now what B2 is, well, they know B1 was a 1. Maybe this had that bit. And in this case, they know that B3 was also a 1. B2 was 0 or 1, and then possibly B. Okay, so what happens now if we look at B2? If B2 was a 0, and again, P1 doesn't know what this bit was, but if it was a 0, and this came out to 0, that means P2 had to transmit a 1 here. Right? So 1 plus 1 mod 2 is equal to 0. So if B2 is 0, then person 2 was the one who sent the bit. On the other hand, if B2 was a 1, then if this was a 1, 1 plus 1, that means that could not have been a 1 because the result is 0. So that means P3 had 1 plus 1 plus 1, mod 2 is equal to 1. So if B2 was equal to 1, then P3 sent the bit, right? So that's as far as P1 can get in their calculations, because if they don't know B2, then they don't know who sent the bit. If they did know B2, they could figure it out, but they don't have enough information because B2 was hidden. That's sort of our hand-wavy proof of this. Questions? Okay. All right, so P1 does not know B2. And if we think about it, if we imagine that B was equal to 0 and we ran the same algorithm with the same numbers, the same random bits, well, we would get P1 is equal to 0. P2 now is equal to 1. All right, so B1 plus B2 is 1. The B bit is a 0. And P3 is still equal to 1. So when we sum up P1 plus P2 plus P3, we get 0, which is the transmitted bit B. And so that works. Now the last question is that still anonymous? Well, in this example, again, we know P1 knows what they transmitted. P1 knows B1 and B3. So when we start substituting back in, well, at this point, actually, person 1 can figure out B2. Since they know bit B was a 0, everybody knows it. Everybody can figure it out. So we can substitute that in there. So that means B2 must have been a 0 because both of these guys transmitted a 1. But that information doesn't help him. He still can't decide if person 2 or person 3 was transmitting, right? Because the B bit is still a 0. So yeah, that's basically the proof in a nutshell. Now, if you really wanted to prove it, you'd have to do, I think there's 6 or 8 cases that look all very similar to this, but I think these 2 examples are enough. Hopefully you're convinced. So basically, we can extend this to any number of people, and then have a network where we can broadcast anonymously and solve problems like, is the NSA spying on you? Things like that. All right. Questions? Okay. So if you're interested in this problem, then I do go over all of the case analysis in the slides, but you don't have to. Yep.
This example of if one person is adding a bit, multiple people they change.
Yeah. Not this example. I would have to look up this larger branch of mathematics to figure that out. Geez, I did read this a while ago, but I don't remember the answer. Yeah, in this case, it has to be that only one person is broadcasting. So in some sense, it's very limited what you can do with it, but yeah. Other questions? Okay. All right. So yeah, this is essentially, if you're interested, all this, I mean, it's even more tedious than everything we just looked at. So but that's up to you. It does break down in the sense that either the person that's trying to figure it out does not know the third bit and so cannot figure it out, or else they can figure out the third bit as in here, but that information doesn't help them, right? So if B is equal to 1, then they don't know the third bit. If B is equal to 0, they can figure out the third bit, but it won't help them to figure it out. All right. All right, so that's just a little warm-up exercise for your brain. Let's get into probability. So this is a lot of, again, we're going right back to counting in some sense. A lot of set theory here. But so yeah, when we talk about probability, we have a sample space. So a sample space is a non-empty set in mathematical terms, but it's also the set of all possible things that can happen. So when we talk about probability, we're talking about, we're looking at some set of events and we want to predict what event might happen. So S is a non-empty set, and we say an outcome is an element of S. So in this particular set, S consists of, or S is the sample space consisting of all possible ways we can flip a coin a single time, right? So it can come out heads or come out tails. Right, so this is a very small sample space, and tails would be one outcome, heads would be another outcome. Right, so now to determine probability, we're going to apply a probability function to all of the elements in our sample space. All that means is we're going to assign them a value, and it can be sort of arbitrary, but there's a couple rules. One is that any value I assign must be between 0 and 1, right? It's a real number, so all the probabilities sum up to 1. We don't talk in percentages, really. We talk in decimals. The other is that, each one must be between 0 and 1, and if I sum up all of the probabilities in my sample space, they all add up to 1, right? So in this case, if I flip a fair coin, I could assign 0.5 to tails and 0.5 to heads. That's my probability function. It's just a value assigned to each outcome. Both of these are between 0 and 1, so that fulfills the first part. And if I add them together, they add up to 1, which fulfills the second part. Right? So my sample space must be complete in the sense that something from that sample space must happen. If I flip a coin, it must come up heads or tails, in our universe at least. So yeah, we assign a real number to each element of S, and all of these probability functions, all of these numbers sum up to 1. Yeah, so if we select an element, or if we run this experiment and we get an outcome, we get it with probability defined by the probability function. Right? And what does this mean? What does this probability mean? It means that if I run this experiment, a very large number of times, it's going to approach a value. So if I run this experiment a large number of times, the proportion of tails and heads will approach 0.5. If I flip it 3 times, then I could, have 2 of one and 1 of another. But if I flip it 1 billion times, it's going to be pretty close to 500 million of heads and 500 million of tails. So yeah. So here's another arbitrary sample space. Here I have 4 outcomes. That's supposed to be omega, but we'll call it a W. W1, W2, W3, W4. I can now assign them values for my probability function. So these values are between 0 and 1. And if I add up all of them, well, I get 0.25 plus 0.25, that is 0.5. 0.3 plus 0.2, that is also 0.5. So this sums to 1. Right, so this is a valid sample space with a valid probability function. Okay, questions on that? Okay. So yes, we have our sample space of flipping a coin, and if the coin is fair, then of course the probability that it comes up heads is 1/2, and the probability that it comes up tails is 1/2. And yeah, this fits our the rules of probability that we set out, is that they have to sum up to 1. I can also, in my sample space, flip a coin twice, right? So I'm doing an experiment. If I flip a coin twice, then there's 4 outcomes that can happen, right? So I flip it once, I get heads. I flip it again, I get heads. That's the first outcome. Or I get heads, tails, tails, heads, and tails, tails. Okay, so now my experiment is flip a fair coin twice, and I have this in my sample space. And each of these can happen with equal probability, right? So when we get to independence and independent events, this will make more sense. For now, well, probably you have a pretty good intuition into it, but we're also just going to accept that each of these happens with equal probability. Okay, so there's my other sample space. Each of these outcomes has probability 1/4. If I sum them together, the total probability is 1. All right, questions? Okay. We can also have events. So we talked about outcomes. If I perform my experiment, exactly one outcome happens, right? You can't have two outcomes happening. You can't have three. You can't have zero. But I can define an event, and an event is some subset of the sample space. So in this case, I can have an event A. A is my sample space is flip a fair coin twice. And my event A is that one of the coins is heads and one of the coins is tails. So I can draw a Venn diagram. Now my event A is simply a subset of S that contains these two outcomes, right? So now again, when I do my experiment, only one outcome is possible. I can't have two outcomes happen. But if either of the outcomes in my event happen, then I say that event A has happened, right? If I flip heads, tails, then I have one head, one tail. Or if I flip tails, heads, then I have one head, one tail. So event A has happened in this case. So if I want the probability of an event, then I sum up the probabilities of each of the outcomes in the event. Right? This is a lot of these rules are similar to what we learned in counting. In this case, you could think of it as the sum rule, right? So these are two sort of disjoint subsets. I'm taking the union of them and I'm adding them together. But in this case, I'm adding together their probability functions instead of just how many there are. So if the probability of an event A is the sum of all of the outcomes in that event, or the sum of the probabilities of all of the outcomes in that event. So the sum of A in this case is equal to the probability of heads, tails, plus the probability of tails, heads. Each of these we said was probability 1/4. So this is 1/4 plus 1/4 equal to 1/2. So for this sample space where I flip a fair coin twice, the probability that I get one heads and one tails is 1/2. Okay. Maybe I do that over here. But yeah, questions on that? Yeah. It's just a variable. So when I write this summation, I mean, I could write this represents, oops. The W represents some outcome, right? So it's just it's supposed to be omega, but I got lazy with the notation. So yeah, it's just a variable. When I say something like this, W takes on all the values in A, basically. Other questions? Okay. Oh, no. Oh yeah, so here, I did do it. So the sample space is all of the possible outcomes, right? So I have it here as a Venn diagram. It's easier to visualize, but I can write it in set notation. The event A is this subset of the sample space. And so the probability of A is equal to the sum of the individual probabilities, which is 1/2 in this case. Okay, so let's look at another example. I'm going to roll a fair die. So now my sample space consists of all of the possible outcomes of rolling this die. So it's a 6-sided die. So all possible outcomes are the values that come up when I roll the die. And the probabilities, if it's a fair die, then the probability is equally divided between these 6 elements, right? And since they must total to 1, so the probability is going to be 1/6, right? They all have equal probability. It's a fair die. The total is 1, so it must be that they're 1/6. So if I sum them all up, I get 1. And yeah, this is my, yes, the definition of a probability function. So now I can take an event A, say we rolled an odd number, right? So again, this is a subset of my sample space. In this case, the odd numbers are 1, 3, and 5. I can also define it using the set notation. I can also define it in English. These are all equivalent, right? When we talk about sets, we can define them in English using sort of predicates and ands and ors for union and intersection. The probability of this is the sum of the probabilities of the individual outcomes. Each of these outcomes has probability 1/6. So yes, probability of A is equal to the probability of 1 plus the probability of 3 plus the probability of 5, which is 1/6 plus 1/6 plus 1/6, which is equal to 3/6 or 1/2, right? Which probably agrees with your instincts in that rolling an odd number, given that there's 3 odd numbers and 3 even numbers, happens with probability 1/2. Okay. All right. So now we're going to get slightly more complicated, but not too bad. We're going to roll 2 dice now. We're going to roll 1 red die and 1 blue die. These are fair 6-sided dice. So now our sample space consists of some pair of outcomes, right? So for my red die, I have the variable I that takes on all the values from 1 to 6. For my blue die, I have the variable J that takes on all the values 1 to 6. So each outcome now of my double roll is a pair. In this case, it's an ordered pair simply because it's red dice and blue die. So what is the size of this sample space now? So this is a counting problem, right? Yeah. Yeah. Exactly. Yeah. So we're just going to use the product rule. As you said, there's 36 outcomes, and how I get it is I'm going to, in some sense, generate all of them, or I'm going to perform a sequence of tasks. In this case, the first task is choose the value for the red die. I have 6 ways to do that. The second task is choose the value for the blue die. I have 6 ways to do that. So using the product rule, I have 6 times 6 or 36 possible outcomes. Okay, so we're right back to counting. And the probability of each outcome, well, again, this is getting a little ahead of ourselves, but each die roll is independent of the other, which means that whatever value I get on the first die does not affect the probability of any value I get on the second die, which means that each of them has equal probability. Since there's 36 of them and they have to sum up to 1, that's 1/36 is the probability for each individual outcome. Okay. So the round brackets means ordered pair, and we say ordered pair here because, well, these are distinct, right? I roll the red die first and then the blue die. Okay, so 36 possible outcomes. I can list them in a table. If I put my blue dice, all of the outcomes along the top, and the red die, all of the outcomes along the side, then in some sense, this is the Cartesian product of all of these outcomes, right? If I take the set of outcomes for the red die, the set of outcomes for the blue die, I take the Cartesian product of them, I get this is, I don't know, 1805 stuff. Probably you don't remember, but I can list all of the possible outcomes, right? So if I roll 1 on the red die and 1 on the blue die, I get 1, 1. 2, 1 is here, etc. And 6 by 6 grid, so there's 36 entries. But really what I want to find now is when we're talking about rolling two dice, we're usually interested in what's the sum of the two values. So we're going to talk about events. We're going to talk about events where we sum up the red and the blue die. So let's rewrite our outcomes as the sum of two dice. Okay, so here I rolled a 1 on the red, 1 on the blue. I add them together, I get 2. Right, so I'm just adding the values of both dice. If I roll 3 on my blue and 4 on my red, I take the intersection of those two. 3 plus 4 is 7. Okay, so I'm mapping each of my outcomes now to some value, which is traditionally how we do roll dice. We roll dice, we're interested in what the sum is. Okay, so now let's take an event A, which is the sum of the red and the blue die is equal to 4. And let's figure out the probability of event A. So if I look at my table here, there's a lot of symmetry. I want to find all of the outcomes where the sum is 4. So I have 3 of them here, right? And I can write them out explicitly. So this is 4 here, but I could write it as 1, 3. This I can write as 2, 2. And this I can write as 3, 1. Each of these is outcome. So A is a subset consisting of 3 outcomes. So I'm going to sum up the probabilities of each outcome. And as we mentioned, each outcome has an equal probability, which is 1 over 36. So this is this plus this plus this gives us 3 over 36 or 1 over 12. So the probability of basically rolling a 4 on 2 dice is 1 over 12. Right, does it make sense? Questions? All right. We can have a second event B. The event B is that the sum is 5. We can compute that probability the same way, but now we are going to find all of the entries where the sum of the red and the blue are equal to 5. There's 4 of them. And yeah, so my set B is equal to these 4 outcomes. Each of these 4 outcomes has probability 1 over 36. So the probability of event B is equal to the sum of the probabilities. In this case, 4 over 36 or 1/9. Okay, so the odds of me rolling a 4 are 1 over 12. The odds of me rolling a 5 are 1 over 9. Simple enough, I guess. And we can extend that, of course. The probability of rolling a 6 is simply 1, 2, 3, 4, 5. 5 over 36. The probability of rolling a 7, 1, 2, 3, 4, 5, 6. So that is 6 over 36 or 1/6. And yeah, you can go on and on. All right, good questions. We're good, eh? Okay, so that's sort of simple starting point examples. Let's look a little more about the mechanics of probability. So I define an event A. A is a subset of S, and the probability of A is the sum of all the probabilities. So S is actually a subset of itself, right? So I can have the event, anything happens, right? So the probability of S is 1, which means that it's guaranteed to happen. And yeah, this is what is the probability that something happens when we run our experiment. So the probability is 1. Something has to happen. Okay, so every time we perform an experiment, exactly 1 outcome has to happen. So the probability of S is 1. The empty set we can also think of as an event, right? So these are sets. These are operations on sets. So the probability of the empty set, or probability of this event, which is I sum up all the probabilities of everything in there, which is 0. And this is, what is the probability of nothing happening or an impossible outcome, right? So yeah, the empty set, the probability of nothing happening is 0. I perform an experiment, something has to happen. Those are sort of maybe not completely realistic assumptions, but that's the mathematical model that we use. Okay, yeah, so we have to select something because of how we defined outcome. All right, questions? All right. What is the probability of A complement? So we've talked a little bit about sets. So we know if we have a set S and a subset A, then if we take everything that is not in A but still in S, we get A complement, right? So we can determine this probability. So what would it be? Yeah, 1 minus the probability of A, right? So everything in S has to sum up to 1. So if I want the probability of A complement, I'm simply going to be subtracting the probability of A. Yeah, so A complement is a subset of S, thus it's also its own event. And we can use what we know of A to determine it, using set operations. A union A complement is the entire set S. These are disjoint subsets, right? They do not share any elements by definition, but they are summed up, they are equal to 1. So then if I want either the probability of A or the probability of A complement, I can use what's in some sense equivalent to the complement rule of counting. But yeah, I can subtract the probability of the complement from 1. Right. Okay. Does that make sense? Any questions? All right. Yeah. And as with counting, sometimes it's easier to compute the probability of the complement. Again, almost everything we do in probability is simply counting, but with extra steps. Counting with a sample space, essentially. If we have 2 events, A and B, and they are disjoint sets, then, well, probability of A is, of course, all of the outcomes in A, and probability B is, of course, all of the outcomes in B. Since these are disjoint, they do not have any outcomes in common. So if we want all of the probabilities of both, we can find the probability of A union B, right? So we're going to take all the probabilities in here and all the probabilities in here. They're disjoint. You remember from the counting, the sum rule, if they're disjoint, we can add up the size of them. But now instead of the size, we're just looking at a probability function, right? So we have a bunch of elements in here, but instead of counting them, we simply sum up their probabilities. So then the probability of A union B is the probability of A plus the probability of B. If A and B are not disjoint sets, then again, we have our parallel to counting. So we have A and B, but they overlap. So there are some elements in here, and they have probabilities assigned to them, some real number. Well, I'm going to, if I was counting them, I would take, the size of A union B equals everything in A plus everything in B, minus this intersection that I've counted twice. Well, the same rule applies to probability. The probability of A union B, well, I take the probability of everything in A plus the probability of everything in B, right? So I'm simply summing up all the outcomes in A and B, which means that I've added all of these outcomes twice. All right, so that means I need to use sort of an inclusion-exclusion rule in order to get to the actual probability. So I'm going to subtract the probability of the intersection. We will see, similar to inclusion exclusion. We'll see an example in a second. Yeah, questions? All right. Okay, so as an example for some of these rules, let's say we have a set S. It consists of all of the numbers from 1 to 1,000. And we'll say that the probability of each possible outcome in S is 1 over 1,000. So they each have equal probability in this case. And so yeah, here's our set S. Now, our event is we're going to choose a random element X from S. Each of them comes with equal probability. So now we want the probability of this event that X is divisible by 2 or 3. Okay, so again, these are, don't get too distracted by this probability function. This defines a set, right? X is divisible by 2 or 3 is some subset of S. And we can figure it out the same way that we would figure out any other subset. So I take all of the elements that are divided by 2, all of the elements that are divided by 3, and OR is basically equivalent to the union of these two sets. So I want to count everything in the union, which means that I have to account for all of the ones that are divisible by both 2 and 3. Okay. So yes, here when I defined this set, X is divisible by 2 or 3, so I'm taking the union. When I look at the intersection, these are all the elements divisible by 2 and 3. So in this case, that means they're divisible by 6. All right, so what is this probability? Well, I'm going to, define two sets. Set A is all the numbers divisible by 2. Set B is all the numbers divisible by 3. And we can sort of count them without too much trouble, right? So A has size 500. B has size, let me think here. What is that, 333? Yeah. So then the probability of A plus the probability of B minus the probability of A intersect B. Well, the probability of A is simply each of them has an equal probability of 1 over 1,000. So it's going to be the size of A times 1 over 1,000. Right. So in this case, that's 500 over 1,000. Let's see. Now the probability of B is 333 times 1 over 1,000. So that's 333 over 1,000. So how many numbers are divisible by 6? Oh, grief, what is that? Well, I have it written down here, but maybe I want to take a stab at it. So how many times does 6 go into 1,000? Yeah, it's 166. So if you divide, so it goes in 600, it goes into 600, 100 times, and it goes into 466 times with some left over. So yeah, we don't care about the leftovers because they represent numbers that are outside of our range of 1,000. So I believe it's 166 over 1,000. Okay, so then we can compute that, and I think I do it here. Yeah, so 667 over 1,000. Once we have the 3 values, we can compute the, using our inclusion exclusion. Okay. So yeah, the probability of pulling a random element from 1,000 elements, and that element is divisible by 2 or divisible by 3 is 667 over 1,000. Any questions? Yeah. It's 1,000 divided by 6, but then we drop the remainder, right? Because so it basically it's 166.6. So what is it, 996? Does 6 divide evenly into there? 139. Yeah. So 6 divides into 996 once. 39 is 6. 36 is 3. So yeah, 6 divides evenly into 996. But that's 996 is the last number in this range of 1,000 that it divides evenly into. Right, so if I count all the numbers from 1 to 1,000, that are divisible by 6, I get 6, 12, 18, and the last one I get will be 996. Yeah. Makes sense? All right, other questions? All right. Moving right along. Okay, yeah, let's look at some other examples of probability. And then we might actually start on uniform probability, which is basically almost everything is uniform probability as long as we define our sets right. But yeah, so let's do a couple of exercises. So consider a coin that has a 0 on one side and a 1 on the other. We're going to flip this coin once and roll a 6-sided fair die twice. And we're going to take the product of the 3 numbers. So we need to define the sample space. Yeah, so simple enough. I can define it in terms of just a triple, right? And then I can map that triple to some value, the same way we did with the red die and the blue die. So the first number in my triple will be the coin flip. So that'll be 0 or 1. So yeah, let's say we'll call that I. The second number will be rolling a die. We'll call that J. And the third number will be rolling the die the second time. So we'll call that K. And 0 is less than or equal to I is less than or equal to 1. So there's 2 possible outcomes. 1 is less than or equal to J is less than or equal to 6 for the first die roll. And for the second die roll, we also have 6. So now, what's the size of our sample space here? Yep, 2 times 6 times 6. So we're using the product rule again. So I have 2 choices for the first one. I have 6 choices for J, and I have 6 choices for K. So that is 72. Right, so my sample space consists of 72 elements. And each of these, it asks for the product of the 3 numbers. So then I would have to define, so this would be sort of my starting point. What they want is the product. So I would now define each event as being possible products, right? So if I have, for instance, 1 or 0, 1, 1, that's going to be equal to 0. So anytime I flip my coin and I get a 0, the outcome is going to be 0. So if I count all of the elements in this, let's call this event A equals coin is 0. Then I have 1 choice for my first element, which is 0. I have 6 choices for here, which is my first die roll, and I have 6 choices for there, which is my second die roll. So then the size of A is equal to 1 times 6 times 6, which is 36. Okay, so then if I wanted to determine the probability of this event, so when I'm talking about events and outcomes sort of interchangeably, or in some sense, I'm mapping a set of outcomes that have equal probability to a set of outcomes that don't necessarily have equal probability. So, right, so this is the outcome. Everything that's 0, there's 36 of them, and there are 72 of these total. So my probability that coin is 0 is equal to 36 over 72, which is equal to 1/2. Right? Coin is 0. Oh, sorry, this should be product is 0, which is equivalent to coin is 0. That's almost there. So yeah, this is coin is 0. Oh no. Yeah. Sorry, never mind. Product is 0. Okay, so I've basically taken a sample space where everything has the same probability, and I'm mapping it to another sample space where things are a little skewed. So this is all of the outcomes that are 0, and it has probability 1/2. Okay, and then the other outcomes, well, my coin can also be a 1. It has probability 1/2. And then I'm going to count all of these possible outcomes. But now, if I wanted the value of these, yeah, I would have to take the product. So let's say I wanted all of the probability for 1s. Well, I would simply, yeah, I have one way to choose this, one way to choose this, one way to choose this. I have 72 outcomes total. The product of this is equal to 1. So the probability that I get a 1 is 1 over 72. Makes sense? I'm kind of maybe going a little fast, but if I wanted the probability that, if I'm going to give myself some space here. Yeah. So if I wanted the probability of 2, I would look at all of the outcomes where my product is 2. So this is 1, 2, 1, or 1, 1, 2. Each of those has a probability of 1 over 72. So this is 2 over 72, or 1 over 36. Right, so probability 1, 1 over 72. This is probability 1/2. Probability of 1 is 1 over 72. Probability of 2 is 1 over 36. So yeah, I can, and I can keep going like this. Of course, these are going to start to, the events that are sort of defining my outcomes in my second set are going to be growing in size, but they all have a uniform probability at the base. We just have to count how many outcomes are there. Yeah. Questions? Yeah. If you wanted to answer this, yeah, you'd have to show every single event. So I mean, the product can go up to 36, eh? It's a bit of a pain. But yeah, you would have to, if there's a simpler way to do it, I'm not sure off the top of my head, but this is the process for, so I can define, you know, we mostly deal with uniform probability, but we don't have to. But in some sense, every non-uniform probability has a uniform probability sort of underneath it that's mapped to that. Okay, let's look at another example here. We're going to take a sample space S, which is equal to A, B, C, and D, and a probability function, yeah, basically a probability function that follows all the rules of probability functions. And then we're going to define 4 events, A, B, C, and D. So A is, you know, just the outcome A. Event B is the outcomes A and B. Event C is the outcomes A, B, and C. And event D is the outcomes B and D. So now I'm given a bunch of probabilities and of the first three events, and it asks me for the probability of the last one. All right, so probability of A is 1/10. So Well, this also means that the probability of small a is 1/10, right? Because the event A is simply the outcome small a. Now the probability B is equal to 1/2. And we know that the probability of an event is equal to the sum of the probabilities of the outcomes in that event. So probability B is equal to probability of little a plus the probability of little b. So we know that little a is equal to 1/10 and the probability of big B is equal to 1/2. So we can simply plug those in and solve for the probability of little b. Okay, so that is 5/10 minus 1/10, so it's equal to 4/10 or 2/5. Okay, and basically if I track down all of my outcomes this way, so now I can determine, I'm given the probability of C, and I can determine the probability of little c using the same method. Let me again insert some space. So the probability of big C is equal to the sum of the probabilities of little a, little b, and little c. I'm probably doing actually too much work here. But yeah, probability of big C is 7/10. Probability of little a is 1/10. Probability of little b is 2/5, plus the probability of little c. So we can solve for that. What is that? So 1/2. So yeah, probability of c is equal to 2/10 or 1/5. Okay, just a little bit of math there. Yeah, so now we need the probability of D. All right, so we have the probability of A, B, and C. How would we get the probability of D? Again, I think I did too many steps here, but for the sake of argument, I want the probability of little d. Once I have that, I have this plus this, so I can determine the probability of the big D, BD. Right. So how am I going to get this probability of small d? Yeah. Yeah. We could also, I mean, I guaranteed I did too much work here because probability of little d is equal to the probability of S minus the probability of C, right? So this is equal to the probability of A, B, C, D, which is S, minus the probability of A, B, and C. Right, so I'm in some sense using the complement rule. So this is equal to 1 minus, well, this is equal to the probability of C actually. So it's 7/10. So yeah, I definitely did too much work, but. So probability of little d is 3/10. Now the probability of big D is equal to probability of B plus probability of small d. That is equal to 2/5 plus 3/10. Seven over 10. Sorry, I just want to double check. Probability C is 1/5. Probability of I'm assuming that's correct. It might be a good idea to, if this was an assignment, I would double check my work by seeing if this summed up properly with everything else, but yeah. So that's, we can go from, a set of outcomes that gave us some events with probabilities, and we could use those to sort of find the probabilities of the individual outcomes. Probably did too much work, but probability should sum up to 1. So probability of, so 7/10 is B plus D plus A is 1/10, and then C, where's little c, is 1/5. Yeah, that sums up to 1. Yeah. So yeah, it wasn't that hard to double check actually. All right. We might stop there today. We can talk briefly about this one, but I don't think we'll walk through it. So if we have 2 pennies, a nickel, and a dime, so I have 4 coins, and I choose 1 coin uniformly at random, and then choose a second coin from the remaining coins, again uniformly at random. And then I define a sample space. Yeah, so I mean, I'm picking out 2 coins that are ordered pairs of pennies, nickels, and dimes. And then I could determine the probability. Of course, now I'm taking it from a fixed set, right? So once I take 1 coin, the probability of the first one would be 1 out of 4, right? So I have 4 coins, I'm choosing 1 at random. And then the probability of the second coin would be 1 out of 3. So there's a slight variation there, but once right, well, for example, I have 2 pennies, so the probability of penny nickel, for instance, 2 pennies, I choose 1, I have 2 to choose from, so that's 2 out of 4. And picking a nickel, well, I have 3 left to choose from, and I choose a nickel, there's 1 nickel, so that's 1 out of 3. So yeah, I would have to list out all the possible outcomes, and then I could figure out all of their probabilities and then sum them up the same way as before. And even though it might not be immediately obvious, they should all still sum up to 1. And if they don't, that's a red flag that you've done something wrong. All right, so that's it for today. Next class, we will talk about uniform probability, which is mostly what we've been doing, but and then we'll get into some more complicated examples.